All right, folks, it's Bass Action back in action here. In this video, we are going to convert the formulas that we used in the previous geometry review videos for arc length and area of a sector. We're going to convert those formulas to a form that'll be more useful for us when we're trying to work with radians instead. So we're going to start here at the top with the original formula that we had from the geometry review, where arc length is a portion of the circumference. Now I have it flipped around in the other way here, but we've got our portion, that's our arc measure over 360, times the circumference of the circle. So what we're going to do in these quick steps here is we're just going to convert all the little parts. So circumference, of course, is 2 pi r. Our arc measure over 360 is going to stay the same. Then when we look at this step right here, we can see that now we can do a little reducing. 2 will divide into 360 180 times, and then that's going to get us to our next step here, our pi r and our arc measure times our 180. Now, doing a little rearranging, keeping in mind that if we have these two separate fractions, we can visualize this all together. I'm just going to group everything a little differently. So I'm going to take the r over 1, and I've got that right here, the pi and the 180 right here, and then our arc measure is now pulled out. What that allows us to do then is look at this portion right here that we can see then is going to be the arc measure in radians. Okay, so basically we've just converted our degrees to our radians. So that means that a simpler formula that we could work with is this S being arc length. So this is still just going to be the length. We're going to have a new variable for this. And then R is still going to be the radius. And then theta is now going to be the angle that we're working with in radians. So instead of using the old formula, the original formula from up here that you used in the geometry review, you can use this simpler one if the angle that you're given is in radians and not easily converted, or it's specifically wanting a final answer in radians. It'll save you a little bit of work. So let's look at an example here. If I have the radius of some circle, okay, is 10 centimeters, and now it's going to tell us the arc length is 18, and it wants us to find the central angle in radians. Well, if we used our old method, we would have to work backwards like you did in that geometry review, and then take your answer and convert that arc measure to radians. But we can do it a little faster with this new formula where we've got this S equals r theta, and we just substitute in. The radius of the circle is 10. The arc length itself is 18. And theta will be our answer in radians. So we've got our theta. That's going to give us an 18 over 10. And then we can just reduce that to a 9 over 5. And that's already in radians. So it saves us a lot of work using this new formula. Just a quick little reminder, 9/5 radians, notice there's not a pi, 9/5 radians is going to be just a little bit shy of 2 radians. So if you think back to the video that we did on converting radians, that's about 2 dots over. So kind of start to be able to visualize about where those 2 dots are going to be. Then the next one, you can see that it gave us a central angle in radians here. Now, if it's not labeled as degrees, you can assume that it's radians, and it's going to tell us that the radius of the circle is 12, and it wants us to find the arc length. So we've got our S equals r theta. So instead of having to go to the effort of converting 7 pi over 10 to degrees and then using the old formula, we can just jump into this new formula and save ourselves some time. So our radius is 12. I'm going to go ahead and put that over 1 because I can see my angle is in a fraction as well. 7 pi over 10. Then I can do a quick little reducing. I'm going to reduce this down to a 6 and this down to a 5. So my final answer for my arc length is a nice exact answer would be 42 pi over 5. And arc length in this case is measured in inches. So that's a lot faster than trying to do all the work in terms of degrees. Okay, the next thing that we're going to do is going to be a very similar process. We're going to do the same thing with our area of a sector formula. So again, we're going to start off with this formula that we did in our geometry review. The area of a sector, remember that's the whole shaded region, that whole piece of pizza, is going to be a portion of the area. So we've got our portion again, arc measure over 360, and the area. Then we're going to, just like we did before, we're going to do a little substitution. Area becomes pi r squared. Okay, then we're going to do a little creative breaking apart. This 360 right here is going to split into this 2 and this 180. Okay, so I've broken this apart in a different way so that we can group this a little differently. So now we've got a 1/2 and r squared, just pulling out the 1/2. The pi is from right there, just pulling it out as its own separate thing, and then our arc measure over 180. What this does for us, similar to the previous little proof, is that this portion here then gives us the arc measure in radians. So again, if we're trying to work with radians, this is going to be an easier formula. So you're going to have two choices of formulas now. So we've got this new formula, and the important thing to remember is that this angle theta is going to be in radians. Okay, so if you're working with radians, you can't easily convert to degrees, or it wants an answer in radians, this is definitely going to be the formula you're going to want to work with. So let's look at a couple examples. It wants to find the exact area of a sector. Okay, it's going to give us a nice radius here, and it's going to give us this central angle. Notice it's not specifically labeled as radians, but if it's not labeled as degrees, it's radians. So we're going to look at our formula. That's going to be the area is 1/2 r squared theta. I'd really encourage you to write the formula, because the more you write it, the easier it is to remember. So the area is going to be our 1/2. Our radius is 6, so we're going to just jump straight into putting in a 36. I'm going to keep it as over 1. The central angle is 3 pi over 10. So now we can do some quick reducing. 2 goes into 36 18 times. I can see that I can reduce again. 18 reduces down to 9. 10 reduces down to 5, and I still have the 3 pi. So my area multiplying straight across is going to give me 27 pi over 5. We're measuring in centimeters here, so area would be centimeters squared. Again, this is way faster than trying to convert that angle to degrees. That's going to be some really weird degree measure, and then having to work with the old formula. The last example that we're going to do here is it's going to give us the area of a sector. Sorry, first started off here with the central angle, and then the area is the 4 pi r squared. So now we're just going to work our formula backwards. So we've got our area 1/2 r squared theta. Now let's start subbing in. The area is 4 pi, 1/2. The radius, we don't know the radius. That's the point of the question. So we're going to fill in that r squared. And our angle that we're given is 2 pi over 9. So we can start cleaning some things up. The 2's are going to cancel. I can see mathematically that these pi's are going to cancel. So I'm going to multiply both sides by 9. So I'm going to get 36 equals r squared. So my radius is simply 6 centimeters. So again, just a lot faster than trying to convert that 2 pi over 9 to the degrees and then work the old geometry formula backwards. So get comfortable with these two formulas, and we'll do some more practice.